We went through yesterday to actually create these red ordered pairs over here was a great deal of taking a value that I know x is equal to, x equals 0, and substituting that into some equation, and then going through my order of operations and evaluating to get a result of -2. Would you guys agree with that? And everything I just said was Chapter 2 information. What we learned in Chapter 2, what we became proficient at in regards to substituting and evaluating algebraic expressions. If you didn't gather everything that you needed to from Chapter 2, this is going to be a difficult concept, okay? Which I think we're going to be okay with, okay? Last class we had some issues with fractions, and those are things, again, that we're going to have to be able to attack and work with. But what I want to make sure we understand is that right now we're seeing in Chapter 4 a great deal of work that came from Chapter 2. When we get to Chapter 5, Chapter 6, Chapter 7, Chapter 8, Algebra 2, Geometry, College Algebra, these other courses, they use this idea here 100% of the time. This is going to be something that is involved in almost every aspect of the next 3 years of high school math that you're going to encounter. Does that make sense? So if it doesn't make sense and you never learn how to do this, can you foresee it those next 3-4 years would be difficult? Okay. So we're going to spend quite a bit of time talking about this stuff to make sure we do get it because it becomes kind of the main principle of other concepts throughout your remaining high school classes. Okay. And that's not just math. We'll talk about a lot of science stuff here as well. So it could impact those as well. All right. So we said yesterday, why did we choose, and because we talked about in the initial notes where it says create a table using multiple independent variables right here, step 1, I talked about yesterday that it doesn't matter what your independent variables are. Here we started at -1, went to 0, went 1, went 2. You'll see in your homework that one question will start at 0 and go 1, 2, 3. The next one will start at -1 and go -1. Maybe it'll jump 0, go to 1, maybe it'll jump 2 and go to 3. So you're not going to see a lot of consistency in what they're choosing here, okay? Because these can be anything that you want them to be. Does that make sense? The X's are independent. Nothing forces them to be something, okay? It's total choice by you. Does that make sense? Okay. That being said, then, when we come down to here, if these X's are complete choice to me, why choose 0, 2, 4, and 6? Okay, and we talked about it yesterday at the kind of conclusion of class. The reason we chose 0, 2, 4, and 6 is because, first of all, 0 is a good one to choose because 0 times anything is going to be what? 0. And when we start plugging things in, that's what we multiply something by. We're going to multiply something by X, so make it 0, let's make the TD multiplication, okay? So we like to choose 0. Well, then why do I choose 2? Why do I choose 4? Why do I choose 6? Okay, so when I look at 2, I look at 4, or I look at 6, 2 is a factor of all those. Or we can say that 2, 4, and 6 are multiples of that 2, okay? Why is that interesting to us? Because right here, there, and there, when I take a multiple of 2 and multiply it by a half, that product always ends up being a whole number, right? You'd rather work with whole numbers, right? Especially if I have to do something else after that. If I have to subtract 2 from something, my hope is that number I'm subtracting 2 from was a whole number. It's just going to make things easier, okay? Is it wrong to use 1? No. If I want to plug 1 in here, okay, I'll do 1 real quick for us. If I put 1 in as my X value, that's going to give me Y equals -1/2 times 1 minus 2. So it gives me -1/2 minus 2 is negative 2.5. It works. Okay? And negative 2.5 is not a terrible number, but eventually those will be terrible numbers, okay, as decimals. Because maybe, I think the next one will have 2/3. Well, what is 1/3? What is that decimal? 0.3 repeating, though, right? So at some point, I've got to chop that thing off. And when I chop it off, it's really not 1/3 anymore. Okay? And it's an approximation of 1/3. So we don't necessarily like to work with decimals when we're graphing stuff. Okay? So if I can avoid that, I'm going to use that. Does that make sense to everybody? Okay? Now, if I graph these, I think we finished yesterday with just writing these ordered pairs. So now let's take those ordered pairs and come over here and graph them. Okay? So I'm going to go 0, -2. So when I graph anything, I'm going to start where? I'm going to start at the origin. So start at 0, 0. And now this number tells me to move left or right, correct? And this one then tells me to move up or down, correct? If it's negative, you move left. If it's negative, you move down. Is that okay? Okay. So 0, -2. How far do I move left or right? I don't, right? 0 says don't move anywhere. -2 means down 2, right? So I'm going to plot that point right there. Okay. So we got that one done. Then we go to the next one, 2, -3. So where do I go from 0, 0? To the right, 2, right? And then where? Down 3. Okay. Remember, you're always going back to 0, 0 to graph these. So 0, 0, go 4 to the right, down 4, right? Okay. Are those 3 points in a line? Yeah. So my hope is that all these other ones are going to fall in the same line. So 6, -5 would be over 6, and then down 5, right? You guys remember plotting points, correct? Okay. So that's good. We can do that now. I'm going to take my ruler or whatever it may be, straight edge, and I'm going to connect them. Yeah, I'm going to draw this line. So the only thing about this program that I don't like is that the drawing feature for lines is awful. All right, that's okay. So I get that line, right? Now think about this. What this means to me then is that that line is representing an infinite number of ordered pairs. Okay? Meaning, I never graphed on this line the x value of 1, right? But if I look at the x value of 1, and I track down, and then back over to see what the y value that goes with it, what would be that y value right here? Okay, and it's negative, right? Does that make sense to what we found over here when I actually did evaluate x to be 1? What was y? -2.5. Does that make sense to everybody? Okay, so we are seeing, even though they might not be kind of explicit in regards to exactly what the ordered pairs are, but right now, let's say if I asked you to evaluate this equation at 3, I'm going to find 3, I'm going to go down, and then I'm going to go, so where I touch that line, and then I'm going to go straight over, what do you think I'm going to get if I put 3 into that equation? -3.5, right? Does that make sense? Okay. What does it look like I should get if I put in, let me fix the line a little bit here, see if I can make it a little bit better so it actually goes through. There we go. Okay. What do you think I'm going to get if I plug in -4 for my x value? If x was -4, what's the y value that goes with -4 on that line? It's 0, isn't it? Think about this. If I go y equals, it was -1/2 times -4 minus 2. What's -1/2 times -4? What's a negative times +2, right? What's +2 minus 2? 0. Isn't that the y value that we're seeing right here when x is -4? The y value is 0. What do you think I'm going to get if I plug in -6? If I plug -6 in for my x, what's the y that goes with -6 here? It's 1. So I go y equals negative 1/2 times 6 minus, or sorry, negative 6 minus 2. What's negative 1/2 minus 6? Negative 1/2 times negative 6. Negative times the, okay, so negative times the negative is positive, right? Yeah. Half of 6 is 3. What's 3 minus 2? 1. Is that the y value right here of 1 that we're seeing on that line? That kind of makes sense to everybody? So what this line is actually representing, everything that I highlight here, is an infinite number of points that maybe my table doesn't necessarily show me, but does exist. Does that make sense? Okay. What I said yesterday is that when you compare your work or your table to your neighbors or something, maybe you use that point there, and that point there, and you graphed it and got that line. But your neighbor could have used that point there, that point, and that point. Did they get the same line? Yeah. Okay. A third neighbor might have used that one. Might have used maybe that one. Do they get the same line with those blue ones? That kind of makes sense? And that's all predicated off of which x's you choose here. Okay. All right, everybody? All right, so let's talk about something else real quick. You guys remember talking about it would have been a day or two ago, we were trying to write the equation, so they gave me the chart, and we were actually trying to come up with that from the chart. And what we did is I asked you, what's the difference between those two numbers? And you said it increased by 2, right? What's the difference between those two? Increased by 2, right? What's the difference between those two? Increased by 2. Over here, then, we looked at the y's, and I asked you, well, what happens with these y's? What happens between those two? -2 to -3. Do you decrease by 1? Does -3 to -4, does that decrease by 1? Does -4 to -5, does that decrease by 1? Okay, let's look at a picture. If I look at these points here, to go from one point to the next that I've got highlighted here, do you decrease by 1 in the y value? And do you increase by 2 in the x direction? Does that make sense, everybody? Do I go down 1 here in the y value? Increase by 2? Does that make sense? So that down 1 is what was seen here in the table, and that right 2 is what we're seeing over here for our x's in the table. Does that make sense? You guys remember, I don't know, you've seen this before. I know you've talked about this concept before. This is called rise, and that's called my run. So when we're doing that stuff in the table, we're trying to find those differences. With the x's, we're talking about the run. With the y's, we're talking about the rise. You guys know what you get when you put those together in a fraction? Rise over run? That's slope. Okay, and that's where this stuff is going. Okay, we're going to start talking about that stuff eventually. So you've got an exposure to slope, and I'm hopefully trying to get us to a point where not only can we understand like how to use the formula for slope and all that kind of stuff, but actually use that knowledge, that information, the values that we get from that formula to really understand what's going on behind the scenes with the math. Does that make sense? I want to make sure that we don't just get numbers back and say, well, that's it, that's the answer. Don't know what it means, but that's the answer. I want you to know what that number means. I want you to know what these, why is this trick over here with finding the common difference in my x's and my common difference in y's, why does that lead me to an equation? It's because of how slope interacts with our ordered pairs and stuff like that. Okay? Is that doable? Key thing on that question, though, not much different than this first one we did yesterday. The key difference was we had this fraction, so I wanted to use multiples of that denominator, right? So come down to this one. Okay, what do you think would be good choices for x? What is one value of x that we always want to choose? 0. Okay. But now let's look at the denominator. Denominator is no longer 2, it's 3. So what do you think would be a good choice for another x? 3 is a good choice, okay? Because 2/3 times 3 will give me a whole number, right? What's another good choice for x? 6, that's a multiple of 3, and then 9, right? Okay? Now, and this is all, it doesn't, so those are fine, okay? But I look at my graph, and 9 is kind of the last x value that I'm allowed to use on my graph, right? Now, just depending on how much I'm at, I think it's going to be okay here. What we would end up with if I chose 9 is that I will graph a y value of 10. So it actually, like 9, 10 would actually be plotted like right there. Does that make sense? Okay. It's kind of the limit of my graph that I'm allowed to use. But does it make sense is if I use 0 and 3, is -3 also a multiple of 3? Yeah. Okay. Is -6 a multiple of 3? Yeah, so you can use negative numbers as well. So I'm going to do those just because I know they're going to, the y values that are created are not going to exceed what my graph allows for, okay? And that might be something that you guys, obviously at the onset you might not know that, so you might go through some calculations and get some ordered pairs that exceed what your graph is going to allow you to graph. So then you just go back and say, okay, well, let's choose some different x values that may work on my graph. So if you would have gone like 0, 12, and 24, you would have found that only the 0 one would work on my graph, right? So then I don't do 12 and 24. I try something small. Maybe I do 6 and 9 and see if those produce y values I can graph on my graph. Does that make sense? And that's usually if the graph is defined for you. If it's already drawn for you, it's in Math Excel for you, whatever. And if you're drawing it by your hand, you got to construct the graph. It shouldn't matter at all. But in a course exam, the graphs are going to be there for you already. Okay, so I want to make sure that we know how to choose these x values appropriately for that. Okay, so that's all we got to do now is substitute. So we're going back to chapter 2, and we're just going to substitute into this equation. So my y value should equal, 2/3 of -3 plus 4. Okay? What happens, so when we talked about this in the last class, when we were struggling with it, 2/3 times -3. Is that the same thing as 2/3 times -3 over 1?
Yeah.
Okay? If I have, I'm just going to rewrite this way real quick. I should be able to take it as 2 times -3, and I'm going to rearrange the bottom here, 1 times 3 this way. Is that 3 over 3 right there? What's 3 over 3 the same as? 1. So let's cancel, right? And it's going to be -1, yes. But you got 2 left over, right? 2 over 1, and then a negative, so it's going to be -2, correct? That's the multiplication, and we usually do it kind of in our head, or we look at this and say, okay, well, this 3 is in the numerator, and so that black 3 is in the numerator, this red 3 is in the denominator. They should cancel. That's usually what we do, right? And what's the only, once they cancel, what's the only thing you're left with? It's that 2 right there, isn't it? Okay. So you're left with 2. Now it was negative, right? Because that negative didn't cancel. So I have 2 times a negative, so it's -2. What's -2 plus 4? Okay, from -2 plus 4. 2, right? So then when I'm done here, I should have the ordered pair. I started with -3, and it spit back a y value of 2. Okay. The next thing we're going to do, I'm going to go down to 0. Okay, this was one that should be easy. What's 2/3 times 0? 0. Anything times 0 is 0, right? Plus 4 then would be 4. So the ordered pair I get there would be 0, 4. What if we go with 3 here? So you go y equals, and this is why I like to use in this situation, I already used -3, right? So now I'm going to use 3. The math should be the same, except for I got one less negative, right? Okay, so 2/3 times 3 again is, careful, 2/3 times 3 is 2, right? Those cancel. What's 2 plus 4 now? 6. Okay, so the idea of using that -3 and that 3 again is because that math right there and that math right there, other than the negative sign, is exactly the same, right? So why reinvent the wheel? Why try to do new math when I've already got old math that can kind of take its place? Okay, so now I've got the order pair 3, 6, right? And we'll do one more. We'll do 6. Okay, so now I go 2/3 times 6 plus 4. Now, this is usually what we do. How many times does 3 go into 6? 2 times. Okay, so that's going to leave me, what's 2 times 2 now? 4 plus this 4, so it gives me 8. So you get the 0.6, comma, 8. Is that all right? So we can go over and plot those. And tell me, guys, if I'm going too fast with plotting points, you need me to slow down, let me know. If I go from 0, if I need to speed up, let me know. If I go from 0, 0, where do I need to go to plot that first point, -3 to? Left 3 and up 2. Okay. 0, 4, would you guys agree I don't move left or right at all? And we'll go up 4. Okay. 3, 6 would be to the right 3 and up 6. And then 6, 8 would be to the right 6 and then up 8. So right there, correct? Okay. Now, if you remember at the beginning, I did put this blue dot up here. Okay, now I haven't done any algebra for that blue dot. So let's think about this. If I take my line and I draw my line through here, does that line end up passing through that blue dot? Even though I never did the algebra for that one? Does that make sense? Okay. So some people might have said, well, I'm going to choose, maybe we ignored the fact that I wanted to choose multiples of 3 here. Okay. And maybe they chose x to be 1. If you choose x to be 1, let's kind of look at what this would be. It'd be y equals 2/3 times 1 plus 4, right? Well, 2/3 plus 4 ends up being 4.6 repeating, doesn't it? So there's my ordered pair, 1, 4.6 repeating. If I ask you to look at this graph, okay, these red points were easy to graph because they were integer coordinates, meaning that there were no fractions to them, right? If I ask you to go to 1 as an x value, go over to 1 as an x value right here, and then go up to 4.6666666666666 repeating forever, would you have a hard time finding that exact position? Does that make sense? Won't you have to kind of guess where 4.666 repeating is between kind of that line right there and that line right there? Between those two lines, you'd have to guess where 4.6 is, right? Okay. So that's why it's useful to avoid x values that are not multiples of your denominator. Does that make sense? Okay, because using multiples of your denominator eliminates the guesswork of having a graph. Okay. However, though, we see graphically that point does show up on that line, which is a good thing. Okay, that's what we need. Okay. If I were to try to, let's say, look at the x value of 4. Look at the x value of 4. And see where that intersects my graph right there. What do you think the y value would be that goes with an x value of 4? What do you think that y value right there is? 6.8. Would you agree that point right there maybe looks like it's kind of the same position as that one is between 6 and 7, like this one is between 5 and 4? That make sense? Wasn't this one at 4.6 repeating? So is this one, do you think, maybe at 6.6 repeating? Let's see if that's true. Let's do the algebra. If I go 4, so y equals, what was it, 2/3 times 4 plus 4. Okay? This gives me, when I do that multiplication, nothing cancels, gives me 8/3 plus 4. Does anybody know what 8/3 is? 3 goes into 8 2 times, right? Leaving me a remainder of 2. So I get 2 2/3. What's 2 2/3 as a decimal? And then plus my 4, right? Is that 6.6 repeating? Is that exactly what we kind of expected to see as that word pair right there? 4, comma, 6.6 repeating? Does that make sense, everybody? Okay. So when this is a word that you're going to hear me say periodically, when I'm trying to find points inside the data points that I chose over here, so would you agree that my list of values here existed between -3 and 6, right? So -3 and 6. So let's look at just highlighting things between -3 and 6 on my graph. So if I look at just that stuff right there, would you agree that looking at an x value of 4 is inside that blue region? Okay. When you are trying to find a value or some type of relationship between a value that is inside the range of a list of data, like I've done here, okay, 4 should fit in this list of data somewhere. Does that make sense? Should fit on the inside of this list. That process is called interpolation. Okay? When you use a pattern to come up with an unknown value that is inside the list of numbers that you know. Okay? Would you guys agree that this x value of 9 is outside, everything over here in green is outside the list that I had in my chart? Because my list went from, -3 to 6, right? So 7, 8, 9 are outside that, correct? Well, I use my line to predict what that answer right there was, or that word pair was, 9, 10, okay? That process is called extrapolation. Okay? So when you're looking for unknown values on the inside of your data, by using the pattern that exists within your data, it's called interpolation. When you're looking for data points or information outside your given data, based on the patterns that are showing up, that's called extrapolation. Okay? The way I remember that, I learned the two words, but interpolation starts with IN, right? And that information was inside the data that I had, or the data that was provided. That's not going to be a word. I would be probably 95 to 99% confident that those words will never be used in like the end of course exam. But you might hear in a science class, they might say extrapolate this. Well, that means predict what's going to happen later on. Okay, so the idea in a science class is if, let's say, we just put a solution on like a Bunsen burner and we start looking at the temperature, and I just measure the temperature at 0 minutes, 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, and I collect that data and I graph it, and then they might say extrapolate what the temperature would be at 10 minutes. Well, 10 minutes was something that I haven't realized yet, right? I never made that measurement. So I would have to use the information, my data, and the pattern that my data was showing to predict what the temperature is going to be at 10 minutes. Does that make sense? Okay. What if it said use that data of 0, 1, 2, 3, 4, 5 minutes and interpolate what the temperature would be at 2.5 minutes? We never measured what it was at 2.5 minutes, right? We measured at 2 minutes and 3 minutes. But I can use the data that is there to help me predict what it would have been if I measured it at 2.5 minutes. And those are things that you might do in a science class And at that point, my argument is they might not tell you what extrapolation and interpolation means. It might be just a concept that they assume to be common knowledge, okay, because of your math backgrounds, okay. We cool with this process here? All right. Again, if we look at the common differences here, that goes +3 each time, right? And those were my x's. If I go from that point right there to that point right there, do I go 1, 2, 3 to the right? If I look at my y values, they are +2 each time, right? Do I go up 2? So I get from that point there to that point there, I go x value changes by 3, y value changes by 2. Over 3, up 2. Over 3, up 2, right? So that's, you guys talked about that being slope in the past, rise over run. It's that common difference, the change in x's compared to the change in y's. Well, all right? Now, I know, so this is just me kind of spitballing here. I know we're going to struggle with fractions. Okay, it's inevitable. I have seniors that I've been preaching this to since they were freshmen, to work on your fractions, to quit trying to avoid them, because you're always going to struggle with them if you avoid them. Okay, my thought though, so hear me out on this. First time you started working with adding, subtracting, multiplying, dividing fractions was 5th grade. Okay, so this is a 5th and 6th grade standard, and we still struggle with it. Okay. But the reason for that is because when it didn't make sense then, we were allowed to grab our calculator and let our calculator do everything. And then we never took the initiative to wean ourselves off that calculator and actually learn how to do the algebra. Does that make sense?
I thought it was like 3rd grade.
Okay, it might have been early. You start learning what like halves and stuff like that are pretty early. But doing the actual arithmetic with them is probably 5th and 6th grade. I made a comparison in the last period. You know, I like my breaks. I like Christmas. I like Thanksgiving break. I like summer. But what's the worst thing about break?
You forget everything.
Well, you do. That happens. What's the worst day of like summer break?
The last day.
The last day, right? Because you are dreading coming back to school, right? Okay. But when you get here, you kind of get through it, right? It's not as bad as what you thought it was going to be, right? Fractions are the same way. You might dread seeing a fraction. You might dread working with it because you're just afraid of it. Okay, there's unknown there, right? But once you meet that face to face and start actually working with them, you'll find out they're not that bad. They're not that hard to work with. Okay, but you have to be able to push yourself to do that, right? Okay, I made the analogy. You know, you guys have to do chores at home.
Yes.
Okay, when you get a list of chores and I do this with my daughter all the time. Like, wow, let's pick some stuff up. Let's get the house clean, all right? And she throws a fit. All right? I said, well, I'll help you. And we start helping, and then she starts loving it. And she starts, like, how fast she can put stuff away. And by the time that we're done, she enjoyed herself, right? You know, she's 5, so not everybody's going to enjoy it. But once you start doing your chores, does that dread that it was initially there kind of vanish a little bit? Yeah. It's the same thing with fractions. Same thing with any math, okay? Once you expose yourself to it and start working with it, it's not that bad, okay? So if you struggle with fractions, quit using your calculator to avoid them, meet them head on, and you're going to find out, oh, I wish I would have done this about 2-3 years ago because it would have made things so much easier from that point to now, okay? That being said, I want you, if you are a person that struggles, use your technology wisely to help out. Okay? Wisely. That means do the work by hand first, and then go to something like Desmos and verify it. If I put -3 here, do I get the 2 back that I had right there? Okay, so what was the next value I chose? 0, right? Does 0 produce a 4? If I put 3 in, does 3 produce a 6? And if I put 6 in, does 6 produce the 8? That kind of make sense? Okay. I want you to use that responsibly. I want you to understand that is something to check that you've done this stuff correctly. Okay. When you get to the end of course exam, will you have that calculator? Yes, you will. Okay, so here you'll have this calculator in the end of course exam. So here's my thought to you on the end of course exam. Use the calculator. Does that make sense? Because we're trying to pass that test, right? Okay, so when I preach to you from day one, let's use mental math. Let's get better at those skills. Okay, because I understand how those things are going to get better at those skills are going to help you in other classes. Because the end goal is not always the end of course exam. Does that make sense, everybody? The end of course exam is just a hoop that we have to jump through. Okay, and we have to successfully jump through it. But when we get to that thing, let's not rely on maybe a skill that we haven't refined 100% yet. We're continually working on refining that. We know the calculator is going to work on our end of course exam, right? Let's use it. All right. But if I don't use Desmos from here until the end of course exam, will I be able to use it? No, right? If you don't know how to use the tool that you're going to be asked to use, you're not going to be able to be efficient with that tool. Okay? Just kind of keep those things in mind. So Desmos on your end of course exam, that Ohio browser thing, whatever you download to get into those exams, has that built into it. It has. Now there's going to be some aspects of it that they cut away. I don't know if, I doubt your ABC stuff will be there. This will be there. I don't know how much of this function stuff will be there, but you'll have a version of this calculator. Huh? Yes. All right. Here, so what happens is, obviously we've done these two examples to work with this concept, but there was no context, there was no story to those problems. Okay. Here we're gonna have a story. Okay. Somebody's got a bank account, and that bank account's growth, the way it's changing, is based off of this function y equals 7.25x plus 300. Okay. It talks about how 7.25 is their hourly wage, so that's what they're making per hour. And wants to know after X amount of hours, how much money is in their bank account. So let's just say that after I work 1 hour, my employer puts $7.25 in my account. After 2 hours, it puts another 7.25 in my account. And it just keeps doing that, right? The money never gets direct deposit, never comes to me. We want to see how does that bank account grow. These numbers are going to be nastier, okay? The more that we use math to represent like real life situations, real life scenarios, the more applicable the math is to real life, the messier the numbers get. Okay, really nothing in nature or the environment really works out to use really, really nice, clean, whole numbers and stuff like that. So you're gonna get fractions, you're gonna get decimals, all that kind of stuff. That's fine. Okay. So if I use 0, so let's talk about what 0 is. Y equals 7.25 times 0 plus 300. What does 0 mean for an x value? It means 0, but what does it mean for my statement up here? How many hours have I worked? 0, right? I haven't started working this week or this job yet. So this 300 means what? Is that money that I've earned per this job, or is that just what I started with in my account? That's what you started with in the account. Does that make sense? So maybe that was your savings from like birthday gifts or whatever. You put $300 in the account, and then I've worked no hours. My account this should make sense. 0 hours of work, and you have $300. Okay. But now if I work 10 hours, how does that multiplying by 10 adjust this decimal right here for 7.25? Move it over which direction? To the right. So 7.25 times 10 is 72.50, right? So at 10 hours, I should have $372.50. Is that okay? Yeah. All right. I'm going to skip this 15 one for a moment. Let's come down here to 20. Because multiplying by 10 was pretty easy, right? Multiplying by 20 should be just as easy. Because if I multiply by 20, is that similar to multiplying by 2 and then by 10? So what's 7.25 times 2? 14.5, right? 14.50. Well, now multiply that by 10. 145, right? would you have thought right away when you look at 7.25 that you'd be able to find that product, 7.25 times 20, is 145 that quick? But if you already know, if you know what, 2 times 10 is 20, right? So 7.25 times 2 times 10 is the same thing as 7.25 times 20. You should be able to break it down that way and get 145 for that right there. So 145 plus 300, 445. So 220, 20 was the number of hours, and then 425. 445, is that what it was? Yeah. I'm sorry, 445. Yes, 445. That's the amount in my bank account, right? Now think about this. Is this a linear function? We said yesterday if this exponent was 1, it was going to be a line, right? Okay. Does 15 fall halfway between 10 and 20? Does that make sense? So when I have 15 right here, the y value that goes with 15 is going to fall halfway in between those two. Does that make sense? That's the pattern that we're trying to use. That would be that's that interpolation idea, and you can verify that by taking 7.25 times 15 plus 300. Okay, or you can add that one and that one together and divide by 2, and it gives you the midpoint. It turns out to be 408.75. And then if I've done 20, I should be able to do 40, just as easy. 7.25 times 40 plus 300. 7.25 times 2. Okay, good. It's 29. So 7.25 times 4 is 29. So then multiply that by 10, and it gives you 290. So 290 plus 300 then is 590, right? So here's my thought. If we go through it and do that math and try to get better at that, I think just doing that practice right there, we learn some mental math. We learn a little bit of distributed property. We get better at being able to being that kind of that human calculator. But should I also maybe take the time to make sure that I've done that math correctly? So let's put, obviously, 0 in there. Gives me 300. Let's put 10 in there. It gives me 372.5. Let's put 15 in there. 408.75. Put 20 in there. 445. Put 40 in there. 590, right? So those data points are confirmed that way. I'm telling you to use that responsibly. I think in the past, maybe your teacher said use it. Okay? But they didn't tell you how to use it. And we've used it incorrectly, and it's harmed us algebraically. I want you to use it responsibly so that you learn something from it. Okay? Now, I want to graph these. So do you ever want to graph out to 590 on your y-axis? No. So it makes sense to maybe go by 50s. Or by 100s. Okay? My first y value that I'm going to plot here is 300, right? So this is kind of what I'm going to do. I'm going to put 300 right there. And then we'll go by 50s after that. So 350, 400, 450, 500, 550, and then 600. Is that okay with everybody? Have you ever seen a graph that did something like this? Where right here they kind of break the axes, they bend the axes and make it look crooked. You ever seen that before? What they're trying to show you here is that if I look at that blue distance, would you agree just the size of that blue, that it's the same size as that orange, which is the same size as that green, which is the same size as, what happened? Which is the same size then as that green, which is the same size as that blue. Would you guys agree that those intervals there are the same? Same length? How many values are between those two, between 350 and 400? 50. How many are between those two? 50. How many are between these two of 0 and 300? 300. Do you see how that interval, even though it's the same width or the same length, it's got more values in it? To make sure that you are aware of that you pay attention to that, your graph is going to have that little break in it down there close to where they intersect. Does that make sense? And that's just making you visually aware that we've done something here a little bit different than what we're seeing for the rest of this. Okay? My x-axis, maybe I go by tens. Okay? If you were to plot these points, so 0, 300, 0, 300 is right there. Okay, 10, 372 and a half would be, kind of got a guesstimate here, maybe there. 20, 445, maybe about right there. 15, 408, maybe about right there. Does that make sense? And then 40, 590, maybe about right there. Do those purple dots look like they're in a line? Yes. Okay. So when your X's and Y's kind of exceed traditional graphs, you might have to do something like that.